Okay, good morning. It's September 29, 2023, and the time is around 2:50 a.m. Okay, this is Professor David Delos Reyes. My topic for this session will be a continuation of my discussion on alternating current machines, and I am now on lesson number 25. We are now on lesson number 25. So for those of you who are following my channel and watching my topic on the AC machines, good morning and let's proceed. The subject matter for this morning will be AC machines, lesson number 25. We are running smooth, okay? And the title of the topic is copper loss computation, okay? By using the derived formula the last time around. That is, copper loss is equal to a certain constant K times the square of the kVA. Okay? So, this is actually the other formula for the computation of the copper loss, right? Because the other formulas is actually by using the equation, the square of the current multiplied by the resistance. Okay? That will be the first one. It's either referred to the primary or secondary. So as another solution, it is by using the formula equal to certain constant K times the value kVA quantity square. Okay, let's proceed. I will try to give you an example problem. A transformer with a rating of 10 kVA. The rating is 10 kVA, meaning the power output is 10 kVA, kilovolt ampere, right? And a voltage rating of 2300 and 230, meaning it's a step down transformer. The primary is 2300 and the secondary is 230, has been short circuit tested. Okay, and the readings are, or the readings were, capital letter A with the subscript SC, meaning the short circuit voltage applied on the primary during the short circuit test is 137 volts. We adjusted this one by using the variac, right? And capital letter P with the subscript SC, meaning the true power or the value of what do you call this? PSC. PSC is actually the wattmeter reading. And the reading is 192 watts. And the short circuit current is capital letter I with the subscript SC is capital letter I with subscript SC is 4.84 amperes. So power short circuit during the short circuit test is 192 watts and the short circuit current is 4.84 amperes. Okay. Calculate the copper losses when the problem specified two conditions. A, when the load is 8 kVA, because originally the load of the transformer is 10 kVA. Okay, but when the load is 8 kVA, what will be the copper losses? And number two, letter B, when the load is 10 kilowatts and power factor is 0.85, okay, 10 kilowatts, it's not kVA, and 0.85, what will be the copper losses? From the look of it, it seems we are given so many things on the problem, but the other data are actually not needed, right? Because in the computation of the copper losses, the formula is just copper loss equal to a certain constant K times the square of the kVA, right? So there is no voltage appearing on the formula, but in the so-called derivation there was, right? It was just as a last resort or last what do you call this permanent formula. It just came out as simply equal to K times the square of the kVA. Okay, let's try to proceed with the solution. To compute for the copper loss at any given load, okay, we must have to compute for the value of K for the given transformer. So if we try to compute for K, it will be copper loss over the square of the KVA, right? We manipulate this one. We solve for K, so we divide both sides by copper loss. So K now will be copper loss over the square of the KVA. Okay? So this will now be the equation on how to compute for the value of K. Value of K is actually depending on the constants of the transformer. Okay? We know for a fact that the power during the short circuit test actually represents the copper loss. Right? We should know this one. So, capital letter P with the subscript is 6 copper loss, and this should be equal to 192 watts. And what is kVA quantity squared? kVA is actually apparent power, right? So, our original apparent power, the original output power of the apparent power of the transformer is 10 kVA. Okay? So, this is given. The copper loss, we got this value here because from the definition of a short circuit test, the wattmeter reading during the short circuit test represents the copper loss. So we place it here as 192 watts. Okay? So solving for K now, this should be 192, which is the copper loss, okay, which was taken during the short circuit test all over the original apparent power. The apparent power, okay, when that copper loss was taken, it is actually 10 kVA. So this is 10 quantity square. 192 over, this is 100. So K will be 1.92. Okay. So let's now try to compute for the copper loss when the load is 8 kVA. Okay. So we are talking the same transformer here. We are only changing the percentage of the load. The load is just instead of 10 kVA, the load is 8 kVA, and the problem is asking what will be the copper loss if the output supposed to be is 8 kVA. So again, by using the same formula, copper loss equal to K times the square of kVA, we now know K, right? So this is 1.92. The new apparent power or percentage load output is actually 8 kVA. So this should be 8 quantity square. 1.92 times 64. What comes out is 122.88 watts. Okay, it is lesser. Why? Because the what you call this, the copper loss varies, or it is directly proportional to the square of the kVA. Okay, the kVA that was inserted here is actually less than 10, so supposed to be the outcome will be less than the 192. So meaning to say the copper loss at kVA is only 122.88 watts. So this will be our answer. Okay, as simple as that one. The last part is this. When the power load is 10 kilowatts, it doesn't say apparent power, right? It doesn't say kVA, it says kilowatts, right? That's why on the last part of the requirement, the kilowatts is given, the power factor is given. Okay, so if you try to use 10 kilowatts in the computation, you are wrong because 10 kilowatts is not the apparent power. Okay, by definition, okay, under the study of AC circuit, power factor is just true power over apparent power, right? So if we try to compute for apparent power will be equal to true power over power factor. So this is actually the one we need in the right formula. So I place it here. The new apparent power, the percentage of loading that is given on the last part, it will be the true power over power factor. So this should be 10 over 0.85, and this is 11.76 kVA. What's the significance of 11.76 kVA? Because if you use directly 10 kilowatts, you are wrong, right? Because on the formula, what is needed is the kVA, the apparent power. That's why we computed first the resulting apparent power if we are given the true power and power factor. Actually, what comes out is 11.76. So this is bigger than 10 kVA. So supposed to be, if we try to square that one, it will be higher, right? So this is now 1.92. Am I still on camera? Times the square of 11.76 quantity square. 192 times 138.4. And what comes out is 265.74 watts. This is the value of the copper loss, okay, at 11.76 kVA. It is greater than this, because this one is only 8 kVA, and this one is 11.76 kVA. And at 10 kVA, it's only 192 watts. Okay, that's it, guys. That's the way how to compute the so-called copper loss at any given load conditions for any transformer. Okay, good morning from Los Angeles. This is Professor David J. Delos Reyes.